Good morning, students. In the last class, I was discussing the distortion concept. Let me read out again for the sake of brief revision. The Fourier analysis defines the signal as the fundamental frequency and its integer multiples as the harmonics. Therefore, the distorted signals contains the fundamental frequency along with the second harmonic, third harmonic and so on, but with reducing amplitudes. Obviously, if the amplitudes do not reduce, then the fundamental frequency will not be having any effect on the signal as such. So, the percent of the nth harmonic distortion is given as the mod value of AN divided by mod value of A1. A1 is the amplitude of the fundamental frequency and AN is the nth harmonics. So, the total harmonic distortion or THD is given as square root of D2 square plus D3 square plus D4 square, that way it goes on into 100%. Obviously, D1 is not there here because D1 is the fundamental frequency. It is D2, D3, D4 which are causing harmonics. And why is it square now? It is like each one is having a negative value also as such. That is what is squared and its square root is taken after its summation. This way, total harmonic distortion is obtained for a given signal. Let me show you an example in the next slide. You can see this example, distortion due to second harmonic. You can see the blue line is the input signal or the fundamental frequency, and the green line is the second harmonic. You can see the green line is having double the frequency of the blue line. And when we have a linear addition of both of these signals, you can see at the right side there is a purple colored line. Now that purple colored or pink colored line is the resultant of the output signal which is containing the summation of the harmonics. Now it is not just a second harmonics addition, it can be more harmonics also present but with the lesser amplitude. Now you can see because of the second harmonic, the shape of the fundamental frequency is drastically changed. You can see it is always a linear addition here. When both have peak, the peak value can slightly increase because the second harmonic is of a lesser amplitude compared to the fundamental signal. But there is during a zero crossover, you can see when the fundamental signal is crossing zero, the amplitude of the resultant signal is not zero. That is because of the second harmonic. That is how you can see the resultant output signal is having a amplitude distortion. Now, inside our amplifier, anywhere if the harmonics are generated or if the harmonics are amplified, even if the input signals harmonics which are at lesser amplitude, if they are amplified, now that amplification of the harmonics is going to cause the distortion of the input signal itself. That is how you can see the output resultant signal is different. Even if it is a unity gain amplifier, if we consider as an example, you can see the waveform of the signal is distorted in the dashed line shown in pink color. Now this is called amplitude distortion. And along with the amplitude distortion, there can be frequency distortion also. That means the frequency of the signal itself can be affected because of the non-ideal behavior of the devices. So, this distortion is actually unwanted in our amplifiers. But to some extent, distortion is bound to occur because of the non-ideal nature of the circuitry. Let us have an exercise now. Calculate the total harmonic distortion for an output signal having the fundamental amplitude of 2.5 volts, second harmonic amplitude of 0.25 volts, third harmonic amplitude of 0.1 volts, and fourth harmonic amplitude of 0.05 volts. You can see here, fundamental frequency is having an amplitude 2.5 volts, then second harmonics is slightly reduced, third is still reduced, fourth is still reduced. It has to be that way. Otherwise, the fundamental amplitude itself will not be predominant in our output signal. But you can see there are these second, third and fourth harmonics present in the signal now. Now D2 is given as 0.25 divided by 2.5. That is A2 divided by A1. That is 0.1. D3 is given as 0.1 divided by 2.5. That is A3 by A1. That is 0.04. Finally, D4 is 0.05 by 2.5. That is A4 divided by A1. That is 0.02. Now, we will have to square all of them and add them, take its square root. So, it is square root of 0.1 squared plus 0.04 squared plus 0.02 squared into 100. We have about 10.95% or 11% is the total harmonic distortion. In the case of a preamplifier, this is actually a setback. Which means, if at all we use a preamplifier and in the preamplifier this much of distortion occurs, it is 11% distortion. That means only about 89% is the pure signal, remaining 11% is distorted. This may not be the expected output in the case of a preamplifier. We have to reduce the distortion. But how to reduce the distortion? If the output signal contains the distortion, how to reduce the distortion? For reducing the distortion, we have to go for a careful design of an amplifier and we will have to find out which are those devices which are causing this distortion within, and we will have to have better performing devices, or the specifications of the devices have to be changed in such a way that even if it is expensive, we will have to get better devices manufactured, or we will have to use better devices in our circuitry. That is the decision which we have to take. In this example, this 11% distortion cannot be tolerated for a preamplifier as such, or even for a power amplifier also. If it is basically for a music or for a public addressing, now if there is 11% distortion, then the song which is sung by the singer, the voice will have a distortion when it comes out of the amplifier. Now the same music may not be enjoyed by the audience if there is 11% distortion. So definitely this particular example cannot be applicable to a regular audio power amplifier. It may be applicable to class B or class C or class AB amplifiers, not at all for class A amplifiers, because in case of class A amplifiers, it is a 360-degree cycle functionality. For the complete cycle of the input signal, the amplifier is going to work. So, if we are using this for class A amplifier, we will have to take additional measure to reduce the distortion at the output. That is the conclusion of this exercise. There is an expression for the second harmonic distortion. The instantaneous current is given by IC, small ic, is equal to ICQ, the quiescent DC current, plus I0 plus I1 cos omega t plus I2 cos 2 omega t. You can see ICQ is the quiescent current. I0 is the additional DC current that is present, maybe due to some circuit limitations. And I1 cos omega t is the fundamental component. Instead of sin omega t, here we are using cos omega t because at times it is easy to derive the expressions using cos function. So, I1 cos omega t is the fundamental component. I2 cos 2 omega t is the second harmonic component. You can see here omega is the fundamental frequency. ICQ and I0 both are DC. They are not AC. But this omega, when it comes into picture, omega is nothing but angular frequency 2 into pi into f. So frequency is in hertz, whereas omega can be in radians. It is the angular frequency. You can see here in the last term, it is 2 omega because it is a second harmonic component. And you can see I2 must be actually lesser than I1 here, because what is this I2? I2 is the amplitude. That should be less than I1 as per our definition of harmonics or as per the Fourier series. So I1 cos omega t is the fundamental component, I2 cos 2 omega t is the second harmonic component. Let us see how to derive an expression for the second harmonic distortion. You can see here we have this maximum peak current IC max. Again we have minimum peak current IC min. And you can see this ICQ, and you can see I naught also to some extent, right? There is this IC min, that means there is this I naught. Additional DC current can be present because our Q point need not be always at the middle of the load line. So here it is ICQ, that is the quiescent DC current. I naught is the additional DC current. Together we have a DC component with the AC. You can see the AC signal is not actually AC, it is above the x-axis there. And again in this AC we have a maximum peak current and minimum peak current. Now using these terms, let us try to derive the expression for the second harmonic distortion. In the curve at point 1, the instantaneous current small ic is IC max. IC max is what now? ICQ plus I naught plus I1 cos 0 plus I2 cos 0. There the angle is 0. So I1 cos 0, I2 cos 0. Let me show you the picture once again. You can see here at point 1, the x-axis is at 0. You can see the x-axis is omega t, that is the angular frequency. We have this pi by 2, pi, 3 pi by 2, 2 pi. 360 degree means totally it is 2 pi radians, as you already know. So this is totally 360 degree, 2 pi radians. Why we have taken cos purposefully? Otherwise, sine will start from 0, it will gradually rise up and come down. At pi, it will come down to x-axis as a 0 crossover. Whereas cos is slightly different. Cos at 0 itself, it will have the maximum amplitude. It is easy to derive expressions using cos function. Only thing is cos and sine will have a 90 degree phase shift, that's all. Otherwise, signal is going to be the same as such. That is why it is easy to derive. That is why cos omega t is taken. So now you can see ICQ plus I naught plus I1 cos 0 plus I2 cos 0. Cos 0 is 1. So we have ICQ plus I naught plus I1 plus I2. This is at point 1. Now at point 2, corresponding to pi by 2, we have instantaneous current IC is equal to ICQ is equal to ICQ plus I naught. Actually, I should make a change here. ICQ max I should write. Let me change it later on, but I am telling you the correction now. This is ICQ plus I naught plus I1 cos pi by 2 plus I2 cos pi. This is at point 2. At point 2, you can see the fundamental frequency is pi by 2, but the second harmonic will be at pi, as I have shown you earlier here. When the fundamental frequency is at pi by 2, now the second harmonics will be at pi. See here. This is now pi by 2, but the second harmonic is already completed. Even though in this picture it is not really very clear. In the left side you can see here. In the left side picture you can see when the second harmonic is at pi by 2, the first fundamental signal is at pi by 2, second harmonic is at pi. Let me annotate this. You can see this point. Here it is now pi by 2. Whereas for this it is already now pi. This way, second harmonic is having a larger frequency than the first harmonic. That is where we are using this in the formula. Let me go back to my slide now. Of course, in this picture, second harmonic is not shown, but you will have to visualize this picture only. Whatever I am showing you right now at the left hand side, you will have to visualize this picture only. So, ICQ plus I naught plus I1 into cos pi by 2 plus I2 cos pi. Now taking cos pi by 2 and cos pi, we have this ICQ plus I naught minus I2. Because cos pi is minus 1, we have minus I2. And cos pi by 2 gets cancelled here. I1 gets cancelled here. Now in the curve at point 3, it is now instantaneous current is IC minimum. IC minimum is ICQ plus I0 plus I1 cos pi plus I2 cos 2 pi, again corresponding to this point. I1 cos pi, but the second harmonic has already come to 2 pi point here. So that way it is now I1 cos pi plus I2 cos 2 pi. It is nothing but ICQ plus I0 minus I1 plus I2, because cos 2 pi is nothing but cos 0, that is 1. Cos pi is nothing but minus 1. Cos pi by 2 is 0, as you already know. So it is ICQ plus I0 plus I1 minus I1 plus I2. Now solving these equations, we get I0 equals I2 equals IC max plus IC min minus 2 ICQ by 4, and we get I1 equals IC max minus IC min divided by 2. We can use these three equations to obtain the values of I0 and I2 and I1. Now you can see I0 is equal to I2, that is IC max plus IC min minus 2 ICQ divided by 4, and I1 is nothing but IC max minus IC min divided by 2. Now what is this I0? The stray DC current. And what is this I1? The fundamental frequencies current component. So therefore now the expression for the second harmonic distortion is given by I2 by I1, because I2 is there, I1 is here. I1 is the fundamental frequency component, I2 is the second harmonic component. So D2 is equal to half of IC max plus IC min minus ICQ divided by IC max minus IC min, mod of that into 100%. This is the final expression for second harmonic component. Dear students, please work out these expression and remember this, because this expression will be generally asked in the test, in the exam as well. It's a simple derivation, there is nothing much. Only thing is you will have to remember this waveform here, and accordingly you will have to mark these points, and at each instantaneous point you will have to measure the current. I told you that using cos it is easy for us to derive this. You can see this. If at all we used sine there, we would have some minor complications here. Of course, using sine also it is possible, but it will take more number of steps here. Using cos it is very easy to derive. Only thing is between cos and sine, we have to assume 90-degree phase shift. But as such, signal is always instantaneous. So it does not matter whether you start from 0 or you start from the maximum IC max here. If it is sine wave, you should start from 0 amplitude. If it is cos wave, we start from the maximum amplitude. That is the idea here. So this is the expression for the second harmonic components distortion. Why I showed you this derivation is, in the previous example here, we already have the values of D2, D3 and D4. It is already given here and we calculate D2, D3, D4. But in the real life scenario, all these may not be available as such directly, because the complex signal is available. From the complex signal, we will have to find out this D2, D3, D4. We can find out D2, D3, D4 using this expression. We can have a similar expression for D3 also, D4 also, in the similar fashion. But it is out of our curriculum as such, because it is proceeding in the similar way to find out D3 and D4. Only thing is the angles here will change. So that was the discussion about the distortion that is occurring inside the amplifier. Now as we are dealing with the power amplifiers, our transistors will always have a larger power to handle, and we had seen this example earlier as P2Q and PQ in the case of class B and class AB amplifiers. You can see in the picture, the amplifier has to be mounted not just directly on the PCB, it has to be mounted generally on the body, and generally the body will have such fins. You can see these aluminum fins, and this is a aluminum structure, a metallic thin structure, and purposely these fins are made so that there is a lot of air circulation, and if the transistor is heating up, that heat will be easily dissipated into atmosphere by means of all these fins. That is the idea here. So this thing is called as the heat sink now. This whole aluminum structure is called the heat sink. You can see these two nuts here. Using these two nuts only, the transistor is mounted. Transistor is at the other side now. Let me admit the student. The transistor is at the other side of the heat sink now, and the heat sink will have such shapes. You can see the nuts also here. So the maximum power handled by a transistor is specified at ambient temperature. Now whenever we say a transistor is maximum power capacity is 2 watts, it means it is at ambient temperature. Whatever is the atmospheric temperature, 25 degrees centigrade or 27 degrees centigrade, in general we take it. At times we take 25 degrees centigrade, at times we take 27 degrees centigrade. In tropical regions or in countries like India where we have hot summer, we can take it as 27 degrees centigrade. At some cold countries, they take it as 25 degrees centigrade. 2 degrees centigrade does not matter much as such. 2 degrees centigrade difference does not matter much as such. So, let us say we have a transistor which is having a 2 watts maximum power rating that is specified at 27 degrees centigrade for the Indian conditions, let us say. Now, I have to use this transistor in the circuit where there will be maximum power PQ by this transistor has to be only 1 watt. This also I have already told you many times. The transistor has to be in the circuit when it is working, it has to be having a maximum power of only 1 watt. But it has to be rated at 2 watts. Because there must be 50% additional safety for the transistor. Now, this transistor should be mounted on a heat sink. When the temperature exceeds the ambient one, then in order to prevent the destruction of the transistor, either a larger heat sink has to be used or the power needs to be derated. We will have to have a much larger heat sink so that the heat will be easily dissipated into the atmosphere. But at times, in such cases, sometimes we may not be able to use a heat sink at all. For example, inside your mobile phone also you will have a power amplifier. There is a RF amplifier, there is a power amplifier inside your mobile phone also. Now you may think inside a mobile phone why a power amplifier is required. Remember, the mobile phone is receiving power in picowatt. Its signals will be in picovolts or maybe still lesser. Now that particular minute signal has to be amplified into milliwatts. Think about pico to milli, 10 power 9. 10 power 9 is the gain required inside the mobile phone. So there, a transistor which can handle a larger power is required, or an amplifier chip which can handle a larger power is required. But it is impossible to use a heat sink inside a mobile phone, because the mobile phone is meant to be a lightweight device, lesser sized equipment, right? You want your mobile phone to be as lightweight as possible, as handy as possible, as stylish as possible, and it should not handle larger power, and it should give larger battery backup, and it should be cheaper also for you. It should have very high memory also, it should have very high speed also, it should have all types of apps also, it should have a camera also, it should have a music player also. What all is the requirement from a mobile phone now? These are all the requirements from the mobile phone now. Now, in such a case, in some of these applications, heatsink cannot be used. Now, if heatsink cannot be used, then the power needs to be derated. In the sense, if at all for a 2 watts power, if at all I have to use a transistor, if it is not possible to use a heatsink there, then I should not use the transistor even at 1 watt. I should use it at much lesser. That is called the power needs to be derated. So, P2 is equal to P1 minus T2 minus T1 into dF, where dF is the derating factor. Now you can see there is a temperature difference when there is a temperature difference and when heat sink is not possible to be used, the transistor should not be used at a higher power at all. It should be reduced. That is the meaning of derating. For example, a 2 watt transistor should not be used at 2 watts at all. If heat sink is not possible to be used, it should be used at a lesser wattage based upon the temperature. That is called derating. You will understand this when I solve the exercise in the next slide. So P2 is equal to, you can see P1 minus T2 minus T1 into dF. What is P1? P1 is the maximum power rating of the transistor. Now T2 is the second temperature. T1 is the ambient temperature. There is a difference between the temperature at which the transistor is going to work. T2 is going to be the temperature at which the transistor is going to work. In that case, we should use the derating factor here and we should multiply by the difference of the temperature, subtract it from P1, we will get a P2 which is lesser than P1. And we will have to use this transistor only at P2, not at P1. If we use the transistor at P1, the transistor is definitely going to fail. It will not have a comfortable lifespan. That is the idea. So now, let me show you an exercise. You can see this curve now. Here you can see case temperature is in degree centigrade, let us say up to 75 degrees centigrade. Here PT is the maximum total device dissipation in watts. And now it is 100%, let us say, when the case temperature is 75 degrees centigrade. Case means the body of the transistor is 75 degrees centigrade. Now when it goes down, see, when the temperature increases, it has to be derated. Otherwise, the transistor will definitely burn out. So this is called derating. Beyond a certain temperature, power needs to be reduced so that the life of the transistor will be increased. So an exercise is determine the maximum power dissipation allowed for an 80 watt silicon transistor if derating is required above 25 degrees centigrade itself by a derating factor of 0.5 watt per degree centigrade at a case temperature of 125 degrees centigrade. Now look at this. The transistor will handle 80 watt of power at 25 degrees centigrade. Now we want it to work at 125 degrees centigrade. If it has to work at 125 degrees centigrade, then there must be a derating factor. The derating factor is given as 0.5 watt per degree centigrade. That is actually the slope of this line. That is defined as 0.5 watt per degree centigrade. For every 1 degree centigrade rise, 0.5 watt needs to be reduced. So in that way, now T2 is 125 degrees centigrade. Now we have to find out P2. Power at 125 degrees centigrade is equal to P1 is now 80 watt. 80 watt minus 125 minus 25. 125 is the case temperature. 25 degrees centigrade is the minimum temperature at which 80 watts is going to be working. Into 0.5 is the given derating factor. Now when we substitute this in the formula, we get the answer 30 watt. What it means? A transistor which is rated at 80 watt at 25 degrees centigrade will not be utilized at 80 watt at 125 degrees centigrade. It can be utilized at maximum 30 watt if the temperature is 120 degrees centigrade. In this way, power derating needs to be done. Think about some areas on earth where temperature is very high, or think about satellites where they are exposed to sunlight always. In the case of satellites, there is no day, there is no night because they keep revolving around the earth. So the temperature of the satellite may keep on increasing. There we have to use the transistors. Naturally, we have to derate the transistors when we use them inside the satellites. Even the satellites will have power amplifiers. Whatever radio beam is received by the satellite, it has to amplify further and send it back to earth. That is how we have the dish antenna network, where we have cable TV channels now because of the usage of the satellites. So this is the way in which power derating is done for power transistors. Let me come to the next portion of our module. We have seen class A amplifier, we have seen class B amplifier, and we have seen class AB amplifier also. Now let us see class C amplifier. I am almost coming to the end of this module. Maybe in the next class I will be finishing this module. So let us see the class C amplifier now. As per our definition, in class C operation, the collector current flows for less than half cycle. So the conduction period is less than 180 degree. That means the amplifying transistor will not work at 180 degree also. In the class B, we had seen that in the push-pull operation, the transistor is working at slightly less than 180 degree because of that crossover distortion. And in class AB, we gave additional bias there which is working for slightly more than 180 degree. Actually in class B, it is exactly at 180 degree, but with the crossover distortion. But now in the class C amplifier, we will further reduce the conduction period. Purpose is what? The purpose is to increase the efficiency of the amplifier further. We had a distortion in class B. That distortion was because of that crossover. We had to compromise with that crossover. Now we utilized a biasing circuit in class AB. Now because of that biasing circuit, efficiency is slightly reduced compared to class B. Now we want to have higher efficiency. We can compromise on distortion now. Later on, let us see how we are going to compromise on distortion. As I already told you, only audio amplifiers require a correct shape of the waveform. Radio amplifiers do not require a correct shape of the waveform. That is because they work like a carrier waveform. They are the modulated waveforms, whereas we will have a signal which is a modulating waveform. The modulating waveform shape has to be exact. The modulated waveform is going to undergo anyhow change in this amplitude. So its basic amplitude as a waveform is not really very important. So this way, in class C operation, the conduction period is less than 180 degree. Now in that case, the efficiency of class C amplifier will be more than 90%. Means whatever power we supply to the amplifier, almost 90% of the power will be utilized by the amplifier. There will be very less heat. If at all the class C amplifier's efficiency is 90%, only 10% is wasted as the heat. So this is class C amplifier. Class C amplifier is intended to amplify narrow band of frequencies on both sides of the center frequency. As I told you, we are going to use this in RF applications. In the case of RF applications, we don't require a wideband amplifier. For example, when your mobile phone is working with the 2.4 gigahertz carrier frequency, we don't require a wideband amplifier for the radio frequency. It can be a narrowband amplifier, as narrow as possible, because it is working only at 2.4 gigahertz. But whereas for an audio amplifier, we will have to use the amplifier right from 20 hertz to 20 kilohertz. So that bandwidth is 20 kilohertz in case of an audio amplifier. In case of a radio amplifier, when this is a 2.4 gigahertz, the bandwidth can be much lesser, maybe a few kilohertz. Even though we are using a frequency of gigahertz, the bandwidth there can be only a few kilohertz. I am going to show you those waveforms or those pictures later on. So class C amplifier is intended to amplify narrow band of frequencies on both sides of the center frequency. The center frequency is the resonant frequency of the parallel resonant circuit connected at the collector of BJT. I am going to show you in the next slide the picture of class C amplifier. Let me show you now itself. So the center frequency is the resonant frequency of the parallel resonant circuit connected at the collector of BJT. You can see this here now. This is a class C tuned RF amplifier. You can see at the base, there is a base supply given by means of a radio frequency choke. I have already mentioned about the usage of RFC earlier. we are giving a negative base bias. You can see here to the base. Now emitter is connected to ground. To the base we are giving a negative bias. Now let me annotate. Let us say I write an input waveform here. When I write this input waveform here, because I am giving a negative bias, normally transistor is off. Base is connected to minus DC supply. Transistor is normally off. Okay, let me write a bigger waveform instead of the smaller waveform, just to indicate the conduction angle. Let us say this is the input. Let me write at the right side. Now this is the input. When this is the input, at the base when negative voltage is given, transistor is off. Now when this transistor will conduct only when the input signal reaches 0.7 volts, right? Let us say, let me change the color. Let us say somewhere here, it is now 0.7 volts. Okay. At this point, it is now 0.7 volts. So, let me change the color again to just shade it. Now you can see, in a 360-degree cycle, now the transistor is conducting only in this region. The transistor will conduct only when the input signal crosses 0.7 volts. Until then, transistor is off. So you can see out of 360 degree, now out of 360 degree, this is the angle at which the transistor is conducting. Now you can see the angle is less than 180 degree. Conduction angle of the transistor is now less than 180 degree. That is why it is now class C. Now you understand the purpose of RF choke, because this RF signal should not go to power supply. Power supply will always be working like a AC ground. That is why RF choke is connected here. This choke always passes DC, blocks AC. So transistor is purposefully kept switched off in the region at which input signal is less than 0.7 and the transistor conducts at 0.7. Now you may think, when the transistor conducts only, output will come here, right? So output will come corresponding to this waveform only in this manner. Let me stop annotating. Only for this particular area you will get the output. Means you may get only an output this much. You may not get this output. I am going to the other side also. Now you may not get this shaded line output at all. You may get only this portion of the output. Now you may think, what is the point in we getting only a portion of the output? I will tell you later on. You can see this L and C here. This is a resonant circuit. You know that inductance stores magnetic energy and capacitance stores electric energy, right? Inductance stores electromagnetic energy, capacitance stores electrostatic energy. So that way, let me move this line up, indicating the conduction angle as less than 180. Now you can see that more than 50% of the waveform is not available at the output at all. But now, only when the transistor is conducting, there will be a current flow through the L, and when the transistor turns off, these L and C together have stored their energy. When the transistor turns off, they will release their energy. That is the idea. So, transistor turns off only for a short duration. At that time, inductance and capacitance will store the energy. Electromagnetic and electrostatic both. Now, when the transistor turns off, they will release the energy to the output. Now, when they release the energy to the output, the shape of the waveform may not be really very accurate. But as I told you, here the shape of the waveform is not really very much important. As I told you earlier, if you travel in a vehicle, the shape of the vehicle is not important. It is the safety by means of which you travel is important. But still, we make our vehicles attractive looking for the sake of beauty and appearance and style. Otherwise, your bike or car or train or bus has to be safe and efficient. Its outer shape is not really very important. Okay? That is a funny example. You can compare with the BMTC buses shapes. BMT buses have many types of shapes. It is not the shape of the bus that is important. It is the safety in which the driver drives it and the speed at which you reach the destination safely, that is important. And the comfort inside the vehicle is important. The overall shape of the vehicle is not important. Same way, here when we use the radio frequency wave as a carrier wave for carrying the information signal, the carrier wave shape is not going to be important because anyhow it is going to be modulated either by means of amplitude modulation or frequency modulation or phase modulation. In that way, information signal's shape is important, carrier signal's shape is not important. There we make a compromise. So inside your mobile phone, at the antenna, you will have a class C amplifier only, because mobile phone needs to be having larger efficiency. Mobile phone should not get heated up when the amplifier is working. For that purpose, in general, wherever we use RF amplifiers, we go for class C only. We don't go for class A. Class A is only for audio amplifiers, not for radio amplifiers. So class C is for radio amplifiers, not for audio amplifiers, because there is a change in shape here. So now the point is, when these two L and C are connected, as you already know, these are the tuning circuits now. Because now this is a tuning circuit, you have already studied the concept of resonance. Because now this is a tuning circuit, it will work well only in the tuning frequency or its resonant frequency. Now, if we need a amplifier inside the mobile phone working at 2.4 gigahertz, we can have a tuning circuit which is working at resonance at that frequency 2.4 gigahertz. That is the idea. So naturally it will be of very narrow bandwidth. So that is why this is called as class C tuned amplifier, because it is tuned to a given frequency. It need not be of a wider bandwidth. Next, it is called as RF amplifier because it is used for radio frequency. So we are using radio frequency amplifier, we are using class C amplifier, we are using tuned amplifier. Three things are there here. In general, the amplifying transistor is off, it will turn on only for a small portion of the input signal. And for the remaining portion, when the transistor is off, the output waveform is obtained by means of the energy storage elements. And these energy storage elements are connected in such a way that they work like a tuned circuit also, because we want a narrowband amplification. Now, if you want a wideband amplification of RF, then you cannot go for this type of circuitry. There we have to have a different type of circuitry. But we are not going to discuss that in our course. That is an advanced concept there. Here let us discuss only the class C tuned RF amplifiers. So you can see three terms here, students. One is called class C, where the efficiency is more than 90%, conduction angle is less than 180 degree. That is called class C. It is called a tuned amplifier because it is for a narrowband application where we use tuned circuit. It is RF amplifier where we can compromise on the shape of the output waveform. Now, based on this, in the next class, we will discuss in more detail about class C amplifier. See you in the next class. Take care and goodbye. In the next class, I may end this module fully. Later on, let us have revision classes. See you and bye-bye.